Okay, so one of the things we need to talk about is that curves can be represented in several different ways, right? So you can have the same curve and you've got different ways to have that same output. Does that make sense? Here's what that's called. Or here's an example. You could have the twisted cubic. So for practice, you should have Mathematica open right now, and you should graph or plot this twisted cubic and look and see what it looks like. This gives you exactly the same as this representation here, right? So what we're saying is these are two different ways to parameterize the same curve. Does that make sense? What's the connection? T is the same as e to the u. So t squared is going to be e to the u squared, but what's e to the u squared? That's just e to the 2u, right? And the same for t cubed. And now if t is in between 1 and 2, then what happens to e to the u? So if t is in between 1 and 2, but t is equal to e to the u, now e to the u is in between 1 and 2. So that means that if we take the natural log, right? Perhaps I did that a little sloppily. So let's see. So if t is bigger than or equal to 1 and e to the u is bigger than or equal to 1, take natural log of both sides. So the right-hand side will just be u, and the left-hand side will be 0. So that's how we get this part right here, that u is going to be greater than or equal to 0. And we do a similar computation to get the right-hand side. Okay? So use the fact that t is less than or equal to 2 to get that u is less than or equal to natural log of 2. Okay? And the connection between the parameters is given by t equals e to the u. Okay, we say that these equations, so this would be equation 4, and this would be equation 5. So these equations are parametrizations of the same curve. So you've got a curve, right? So you've got a curve, and it looks something like, I think it looks like that, I'm not sure. But the curve is the curve. There's just one curve, but there are different ways to parameterize the same curve, right? You could have your parameter be t, or you could have your parameter be u, and still draw out the same curve. Okay. Now, since we have different curves, that begs the question, what happens to our formula for arc length? Because remember, the formula that we had for arc length is that the length is the integral from a to b of the derivative of that position vector. The length of the derivative of the position vector. But this means that r is dependent on the different components that you have, right? So if we switch, and also the domain for t. So if we switch to a different parameter, u, how do we know that we'll get the same answer? And here's the deal. In general, it can be shown that the formula for arc length is independent of the parameterization that is used. Okay? So it's a little bit beyond the scope of this course for us to prove that, but you just want to, it's something that we have to discuss, because whenever you give a formula, you want to make sure that the formula works regardless of the parameterization that you use. Okay? So suppose we have a function. This is the same as just r is equal to f, g, h. Okay? And the derivative is continuous. R prime is continuous, which means each of those components, f prime, g prime, and h prime, are continuous. C is traversed exactly once as t increases from a to b. So this is key, because you could have a parametrization that traverses the curve twice. So imagine if you were doing the unit circle and you went around the unit circle twice. the length should be twice the length of if you just go around once. Does that make sense? So built into our formula is the assumption that you're just going around once. We define the arc length function. Here's the function. The function is the length of the arc up until time t. Does that make sense? So the input is t, and the output is the arc length of the curve where up until time t. Does that make sense? So if you have a specific curve, right, so the further you go, the longer your arc length is going to be. You're just measuring how long the curve is based on where you are in your parameterization. One of the key things to note about this arc length function is, here's a graphic here, really cool, that explains. So as t increases, right, you're measuring more and more of the arc length. Does that make sense? So S of A is always going to be 0 because S of A is saying what is the arc length when you start at A and stop at A. Right? So S of A is always equal to 0. And then S of B is the length of the entire curve. Right? Because your curve is going to have t in between A and B. So the curve starts at A and stops at B. So S of B is the length of the entire curve. And one of the things to note is that if we use the fundamental theorem of calculus, part 1, we can take the derivative, right? So we know that the derivative of S of t is going to be the magnitude of that derivative vector at t, because that is the fundamental theorem of calculus. And that's pretty cool. So that's a good thing to note, is that how it changes with time is the same as the length of the magnitude of that tangent vector.